Okay, in this section we'll consider simple logistic regression when our predictor of interest is now continuous. And hopefully this will give you some insight as to why we need to transform the estimated binary outcome from a proportion to a log odds, why this transformation is necessary to be able to properly estimate logistic regression equations in general to include predictors that are continuous. We'll also talk about something called a Loess plot, which is analogous to a scatter plot presentation with simple linear regression that helps us get a snapshot of the relationship between the log odds of our outcome and the continuous predictor x1. And this will allow us to evaluate whether the relationship is relatively linear in nature, which is an assumption of the logistic regression model. We'll also learn how to interpret the slope and intercept from simple logistic regression models with continuous predictor and translate this into an estimated odds ratio. This will be very similar to what we did in the last section. So let's just take a little bit more deeper look at the background of the underlying model. Why do we have to model the log odds as a linear function of x1? Well, this becomes an issue when our predictor can be continuous. So let's just think about this for a minute. You might say, well, John, the initial summary statistic we had for binary data was a proportion. It's a perfect way to summarize binary data, the proportion or probability of the outcome occurring. So why don't we just go ahead and fit a regression model that estimates the proportion as a linear function of our predictor. And we want this to work for all situations, including the situation where our predictor is measured as a continuous variable. Well, here's the potential rub with this. The potential difficulty is that the way we've defined proportions, they have to be between 0 and 1. So if we're estimating the proportion as a function of a continuous predictor x, we have to have an estimation procedure to give us the logistic regression intercept and slope that estimates them such that it ensures that all predictions of the proportion or probability we get for all x1 values in our sample of data, all of the resulting combination of the intercept plus the slope times every x1 value yields an estimate between 0 and 1 for the outcome of the proportion. And that's actually a difficult estimation procedure to constrain the slopes and intercepts we get such that they always work with the x1 values in our sample data to give us an estimate of the proportion between 0 and 1. That's actually complicated. So maybe your first thought is, well, we can be a little more flexible. What if we turn the proportion into the odds and try and model that as a function, a linear function of our predictor, where our predictor can be continuous? Well, this might work a little better, but here's the deal with the odds. If the proportion itself, or probability, can lie between 0 and 1, then let's think about what the odds can be. Well, let's take the lower bound on the probability proportion. If that's close to 0, then our odds is going to be such that the numerator is close to 0 and the denominator is close to 1. So when the probability or proportion is close to 0, the odds is close to 0. However, when our probability gets large, gets close to 1, the numerator is close to 1, and the denominator will be close to 0, pushing this towards positive infinity. So odds lives on a more open range than proportion or probability, but it's still constrained by the fact that all estimates of the odds are positive. And if we have a continuous predictor trying to estimate intercept and slope such that all predicted odds for all observations in our data set turn out to be positive, is again a tricky estimation issue. So you'll recall, hopefully, from stat reasoning 1, if we take something that lives on the positive number line and log it, the range of plausible values covers the entire number line from negative infinity to positive infinity. So if we translate things to the log odds scale, any estimated value of the log odds is quote-unquote legal, and there's no constraints on estimating the intercept and slope given a range of x1 values in a data set. So this is the most flexible approach, and that's why we do things on the log odds scale. If we were to transform this formulation where we take the log odds equal to a linear function of our x, if we exponentiate both sides and then solve for the p, or proportion, in the log odds, another way to express this equation is like this, that we're actually modeling the probability of proportion as this function here. And you'll notice that this is just another way of saying that no matter what we get for a beta naught and beta 1, and regardless what the resulting predicted equation is for a given value of x1, the numerator of this probability formulation or version of the equation will always be positive, because e is a positive number. And a positive number raised to any power, be it negative or positive, is positive. And the denominator is always 1 larger than the numerator. So this formulation, if we estimate things on the log odds scale as a linear function of our x's, when we translate back to the probability scale, we will always get an estimated probability between 0 and 1. So it's just another way of saying that this estimation process yields legal values. And we'll show later in this lecture set how to convert from the log odds scale to the probability scale. So let's get into some examples with continuous predictors to really solidify what we're doing here. So data here is taken from the 2009-10 NHANES, or National Health and Nutrition Examination Survey, where there's a sample of over 6,400 U.S. residents in these data between 16 and 80 years old. And what I'm going to look at here, based on these 6,400 residents, is the association between being obese and HDL cholesterol level. So the HDL levels in this sample will average to be 52.4 milligrams per deciliter, but range from a very low 11 to 144, which is a very high value. 15% of the sample is classified as obese in terms of using their BMI measurement to make that classification. So the question we want to ask is, can we estimate the association between the risk of being obese and HDL cholesterol level? And we can certainly use logistic regression and estimate a line that relates the log odds of being obese to a linear function of HDL cholesterol. So here in this formulation, P is the probability of being obese, and this is the log odds, and X1 is the HDL cholesterol level in milligrams per deciliter. We can certainly get the computer to do this. The question is this a good idea? The formulation here makes a strong assumption about the nature of the relationship between the log odds of obesity and HDL cholesterol level as measured on the continuous scale. So how can we take a look and see whether this is reasonable? Well, when we had continuous outcomes and a continuous predictor, we could do a scatter plot and see whether it was reasonable to assume a linear relationship between the mean of our continuous outcome and our predictor. What we're actually assuming is linear when we have a binary outcome is the log odds of the outcome as a function of the predictor. There's no way to directly present this, but there's something that a computer can do to help aid us in this investigation. And this here is something called a low S plot, which I think of as a smooth scatter plot, which tries to plot a visual of the observed log odds of the outcome here, obesity, as a function of HDL cholesterol level. What this plot does is for every value of HDL cholesterol level in our data set, it goes to that value, it chooses a small window of values around that, and for all points in that window, it computes the proportion of persons who are obese. And it gives a little more weight to the points that are closer to the value we're estimating this to than the points farther away. It computes that proportion, turns it into an odds, and takes the log of it, and then plots that against that particular value of HDL cholesterol level. And then the window moves over a little bit to the next observed value and does the same thing. And so this plots the log odds in small windows of HDL and connects them, and we can get a sense of what the shape of the relationship is like. And so for the most part, this visual shows something that's relatively linear. You may say, well, John, there's this huge drop-off here, but this is one of the problems with this type of graph. the ends of it can be heavily influenced by one or two data points, or at least a small proportion. So in order to investigate what was going on here, I went back and looked at the data. The 99th percentile of the HDL cholesterol values is 101. So there's very few data points over here that are above 101 milligrams per deciliter, but it looks like not so many of them were obese, so that pulls this curve down. But if we looked at them between the first and 99% percentile cholesterol levels and looked at this function, it would be well described by this line here. So I'm going to go ahead and say it's reasonable to assume this association is linear, and I'm going to estimate an equation using the computer to explain this. So if we use the computer to estimate this results of this logistic regression, what we get is something that looks like this. The log odds of obesity is equal to an intercept of negative 0.05 plus negative 0.033, our slope, times cholesterol level. So how can we interpret this slope of negative 0.033? Well, to start, it shows that, at least based on the sample data, the association between the log odds of obesity and HDL cholesterol level is negative, indicating higher HDL is associated with lower log odds, hence lower risk. But let's interpret this slope. Well, generically speaking, we've said a slope of a linear equation equals the difference in the left-hand side for two groups who differ by 1 unit. So I'll call it HDL plus 1 minus log odds for a group with value HDL, just indicating that these are generically 1 unit apart. And again, we've said a difference in log odds is akin to the log of the first thing over the second thing. So this is the log odds ratio of being obese for two groups who differ by 1 milligram per deciliter in HDL cholesterol level. So if we exponentiate this, we get the estimated odds ratio of being obese for two groups who differ by 1 unit in HDL. So this odds ratio estimate is 0.967, or about 0.97. So this suggests that the odds ratio of being obese for two groups of persons who differ by 1 unit, which is 1 milligram per deciliter in HDL levels, is 0.97 for the higher HDL group to the lower. So in other words, higher HDL subjects by 1 milligram per deciliter have 3% lower odds of being obese when compared to the lower group. And again, where the difference is 1 milligram per deciliter. And this estimate is for any two groups who differ by 1 milligram per deciliter in HDL in our population from which the sample was taken. And it only applies to the HDL values we saw in the data set. So we saw a range, an extreme range of 11 to 144 milligrams per deciliter, and any 1 unit difference in that range, this odds ratio describes the relative odds of obesity. So your interpretation of beta naught, well, beta naught is equal to negative 0.05, and generically speaking, beta naught is the log odds of obesity for persons with X1 or HDL equal to 0. So again, this is just a placeholder because we don't have any persons in our data set, thankfully, with an HDL cholesterol level of 0. We need this to fully specify our regression equation so that we could, for example, predict the log odds for specific groups based on their HDL level, but it doesn't have any scientific relevance to our data set. So whether we exponentiate it or not, this is just a placeholder in our line. You might say, well, I'm interested in comparing the relative odds of being obese for two groups of people who differ by more than 1 unit. So, for example, those who differ by 20 milligrams per deciliter. And to put some concrete numbers on this, how about 100 milligrams per deciliter versus 80? And, well, this will turn out to be like it was in other linear comparisons we made, but let's just write it out to be sure. If we did the log odds when x1 is equal to 100, it's just generically speaking the intercept plus 100 times the slope, versus the log odds when the cholesterol level is 80, it's equal to the intercept plus 80 times the slope. If we take that difference, we get 20 times the slope, or 20 times negative 0.033, which is negative 0.66. This estimates the log odds ratio of obesity for x1 equals 100 to x1 equals 80. If we exponentiate this, we get the odds ratio estimate, which turns out to be about 0.51. So you see that 3% decrease over 20 years compounds pretty quickly. The resulting odds ratio for those at 100 compared to those at 80 milligrams per deciliter is 0.51. Or those at 100 milligrams per deciliter have 49% lower odds. So this relationship is additive on the slope scale, and we'll show in the practice problems how we could do this directly from the original odds ratio without writing things out on the log scale. Here's another example. Data on a random sample of 192 Nepali children between 1 and 3 years old, from the same population from which we've been looking at Nepali children. One of the things we might be interested in is, in this age range, what's the relationship between breastfeeding at this age and the age of the child. We might want to be able to estimate and quantify that so we can compare it to other populations, children 1 to 3 years old. So what we're going to do is we're going to estimate this breastfeeding age association via a linear equation. We'll look at the log odds that a child is breastfed as a function of his or her age in months. So here's a smooth low S scatter plot of the log odds versus age of the child. And the age ranges again from 12 to 36 months. And this visually, there's a little bit of a curve here, but to start, I'm going to suggest that fitting a line is not a bad approximation to what we're seeing. So I'm going to go ahead and do this on the computer. The estimated equation I get looks like this. The log odds of being breastfed is equal to 7.3 plus negative 0.24 times age in months. So again, we have a negative association, at least for these data. So let's try and interpret this quickly now. We won't go through the same detail we did before, but we've said that this slope compares the outcome for two groups who differ by 1 unit in the x, or x is age in months. So this is the outcome function for two groups of children who differ by 1 month of age. And of course we're looking at a difference in log odds, so this is the log odds ratio of being breastfed for two groups who differ by 1 month in age. And that's equal to negative 0.24. If we exponentiate that, we get the odds ratio estimate equals about 0.79. So each month of age multiplies the relative odds of being breastfed by 0.79, or another way to say it, each month of age is associated with a 21% reduction in the odds of being breastfed. Okay? So again, this estimate is for any two groups of children who differ by 1 month of age in this population of Nepalese children between 12 and 36 months old. So here's a question I'll leave for you to do, and we'll go over in the review questions, is what is the estimated relative odds, i.e. odds ratio, of being breastfed for children who are 30 months old compared to children who are 6 months old? What is the interpretation of the slope here? Well, age of children could potentially be 0, so it's not as absurd, except our age range is between 12 and 24 months. We don't have any newborns. So the log odds of being breastfed at birth, or when age is 0, is estimated by the intercept. But this doesn't really estimate the log odds of being breastfed at birth because we don't have any newborns in our data set. We start at 1 year old. So even though there are 0-month-old babies when they're born new, this estimate does not apply to them because we don't have any in the sample we're using to estimate it. So this is going to be a placeholder again that doesn't describe the log odds for anyone in our data set. We could exponentiate it to get the odds for this group, but again, it doesn't describe anyone in our data. One more example. In the last section, I showed you an example where something that could have been measured on a continuum, gestational age, was actually categorized. And I suggested there was a reason for that. Now, I'm not privy to the raw data, so I can't show you an actual low-S plot that I generate here, but I did have the group data by groups of gestational age and was able to come up with these logistic regression estimates. But I just want to show you something quickly here. So I don't know if you recall, but the reference group, there were 4 gestational age groups, was 37 to 40 weeks. And then we had indicators for being 34 weeks, 35 weeks, and 36 weeks, and this was looking at the log odds of respiratory failure. Let's just graph this just crudely for a moment. Suppose this is our category. These are ordinal categories, 34, 35, 36, and then 37 to 41, so I'll just say 37 plus here. So if we start with the reference group, the estimated log odds is negative 5.5. I'm just going to draw this here. So it's negative 5.5. Okay, so then the first 36 weeks, how much larger is this than negative 5.5 on the log odd scale? Well, I'm going to do these in units of 0.5, so it's 2 units larger. So its value is negative 3.5. 36. And then how much larger is 35 weeks in the same reference group? Well, it's 2.8 units, which puts it at about negative 2.7 on a log odd scale. I'm not drawing this perfectly to scale. And then finally, when we get to the lowest gestational age group, it was 3.4 units higher than the reference, which puts it at, and again, this isn't perfectly drawn to scale, but negative 2.1 here. So what I'm showing here is that for the first 3 groups, it looks like the relationship is roughly linear, but then it really drops between the 36 and 37 weeks. So in order to capture this disconnect here between these 3 groups and the full-term babies, instead of smoothing that out, this categorization schema recognizes that difference in trajectory. I didn't draw this very well, but I'm just trying to give you some insight. So sometimes it makes sense to take something on a continuum and model it as categorical if there is not evidence in the data that the association is strictly linear between the log odds of the outcome and our continuous predictor. So in summary, simple logistic regression can be done with binary, categorical, and continuous predictors. When the predictor x1 is continuous, the model estimates a linear relationship between the log odds y and x1, and there are ways to see whether that assumption is met, and there are visual tools for that. The resulting estimated slope from logistic regression with a continuous predictor still has a log odds ratio interpretation, and the intercept a log odds when x1 equals 0 interpretation, although in many cases that's not relevant to our data.